Or crossover means that we can actually try to mix two different individuals, two different policies, and create a new individual out of it. So here is an example. Assume that you have a set of vectors that look like this. So this was your kind of parameters governing your policy in your parent. You can just simply mutate it by changing one of the parameters from 1 to 0. If your neural network was governed by a set of floating point numbers, which usually is, you can just try to modify one value slightly like this. And this becomes a new policy. This is a different neural network. This is a new policy. And this can become your children. So mutation causes movement in the search space. What do we mean by the search space? This is your search space. Search space means the total space your parameters can cover. So within this parameter space, you are trying to find the maximum parameter. And this is your search space. So within your search space, you are causing a movement by changing a particular value of your individual. So your individual changes, meaning that you are causing a movement. Crossover is based on two individuals. So for example, if one policy was based on this parameter, this set of parameters, another policy was based on this set of parameters, you can just exchange their value and then try to create two children out of them, which is not exactly identical to any of the parents, but pretty similar. And these two become new policies. And this often accelerates search early in evolution of a population. And this is an effective combination. But using this or not is completely up to you. So we try to modify the individuals. And what do we do after modifying the individuals? We need to get the score. We need to get the fitness of each generated individual, which is the children. So yeah, you just measure it. In the case of policy learning, you just need to run the policy and then try to see what rewards each policy is generating. And this evaluation is the only link between this classical genetic algorithm and the problem it is solving. So the genetic algorithm behaves independently of what you are, of the problem. The only thing that constrains the genetic algorithm, that allows genetic algorithms to optimize for the task you are interested in, policy learning, is this fitness evaluation. So you need to make your fitness so that this fitness becomes the score of what you are trying to optimize, what you are trying to maximize, which is the, this J function in our case. This function in our case. Okay, so that was a brief overview of an evolutionary algorithm. Oh, one more thing. Okay, so if we just keep generate children, the population will consistently grow. So we somehow need to maintain the size of the population, and that can be done by discarding members, and there are multiple possible killing criteria, such as killing the oldest individual or killing the individual with the lowest score, and so on. And here is some example. So if you actually have individuals, these dots are individuals. Y-axis is the score. X-axis is the parameter you are trying to optimize. So this is like one parameter optimization. If the distribution was something like this, what you are likely to do is to mutate individuals which are higher than the other. So if you select parents which have good values and then try to mutate them, your children individual will be staying somewhere close to this good individual. And for individuals with low values, you will be just killing them. So they will not survive, they will be killed. Only the individuals which derived from good parents are likely to survive, and then they are likely to be more optimized, and you probably will be able to find the global optimum out of such many out of the population of many individuals. So that was like the very basic genetic algorithm, which you can also apply for the problem we are interested in. We'll not only talk about genetic algorithm, the basic genetic algorithm, but talk about different, evolutionary strategies. So again, coming back to this illustration, this problem setting, here your x and y is the parameters you are trying to optimize. So this x and y becomes your gene. The x value, y value becomes your gene. And f, this is your fitness function. So this, given a problem, given a setting like this, let us look at different types of evolutionary strategies. So we just covered about the genetic algorithm, but let us postpone using genetic algorithm for this one a bit, and then look at even simpler evolutionary strategy. So here is the strategy number one. We sample a set of solutions from a normal distribution. And at each round, we set the new mean to be the best individual. So what are we talking about? In this particular simple evolutionary strategy, I am maintaining my population. In the form of a Gaussian distribution. The Gaussian distribution has a mean and variance. I will not touch the variance, but at every iteration, I will be updating the mean. So if you look at these examples, your blue, the blue dots shows a population. They are, each blue dot is an individual within the population. And what happens at every iteration is that your green is the mean that generated all these individuals. And among these individuals, you will be selecting the red, which gives you the highest value among your blue dots. Among your population, they will be the best one always. And in the next iteration, you set the best one, the red dot, to be the center of the Gaussian distribution. So you will always be sampling by updating your mean to be the best one. And you can see how the population actually moves at every iteration. And you see that this is actually pretty good. It eventually goes to the actual maximum, and it's not actually stuck on the local maximum. So this is already showing some potential. So this is a very straightforward, simple evolutionary strategy. It's not exactly identical to the genetic algorithm you have seen, but any algorithm that maintains a population of individuals and that also kind of improves, updates the population at every iteration, in general could be thought as evolutionary strategies. So this is an evolutionary strategy, and this is kind of simplest case. You just update the mean. And now let us talk about applying the genetic algorithm we just talked about. Genetic algorithm we just talked about for for this particular problem. And just to let you know, the slide is available online. I kind of quickly uploaded this to the website, the course website, so you can look at the all these kind of animations from the website as well. And the animations are from one of my colleagues at Google, from David Ha. Okay, in any case, let us try to assume that we apply the genetic algorithm we talked for this problem. For the fitness, we know the score, and for the deletion, let's say that we only keep 10% of best performing solution in the current generation and kill everything else. So we are being very aggressive. We only maintain 10%. And at every iteration, we also select a parent. So we randomly select two solutions from the survivors of the previous generation. So after killing, there are some populations, some individuals in the population, and we randomly select two solutions out of such 10% best ones. And after doing this, we do the crossover. So the new solution, the children, will inherit X or Y from either parent with 50% chance. So this is, how your parent will be selected, how the mutation or the crossover will be happening, and how the deletion will be happening. And if we do this, it looks like this. So initially, we have some random like set of individuals, and you let them mutate. You only survive like 10% of them. And what we mean by 10% is these green dots are showing these 10% best individuals which will be surviving. And out of these 10% individuals, you will be always, checking for the best one, the best performing individual, and that's the red one. So you are always kind of moving the entire distribution. You are always, choosing the parents, modifying the parents, and your best one is kind of changing and converging to the actual maxima. So the optimization will happen this way differently, but they lead to the same thing compared to the simple genetic algorithm. And obviously, for this very simple environment, they lead to the same thing. But depending on the environment, yeah, their power will be different. So this was an application about genetic algorithm for optimization. You are optimizing your parameters, your policy parameters. I mean, here is XY parameters. And here comes slightly more complicated one, but it's not really that complicated in some sense. Okay, what are we doing? Here, so in this very first one, we only cared about the mean. We left the variance untouched. So the variance are just staying similar in this simple, very simple evolutionary strategy. Here, in this approach, we'll be updating the variance as well. So the approach is as follows. We maintain a population, yes, but based on this n best solutions of the current generation, we will compute the mean of the next generation. So this is so far, this is exactly identical to the simple evolutionary strategy, maintaining everything in terms of a Gaussian distribution. So we maintain the populations in terms of the Gaussian distribution. We select the best ones. Well, not the single best one. We select n best ones, and then try to compute the mean out of such n best ones, and then set as x mean and y mean. Pretty simple. In addition to this, we try to update the covariance matrix. So here we are trying to compute not just the single variance, assuming this Gaussian distribution, but we are assuming a Gaussian distribution with a covariance matrix. So we need to compute this value, and this value. And how do we compute it? Well, that's pretty easy because, well, not easy, but here we are using a particular trick. We only consider individuals which are n best. And based on this n best, we compute the covariance matrix based on the previous mean. So this is a trick because until we really update the mean and the variance for the future generation, we cannot really sample. But we don't have the variance to sample, so we don't have the samples. So in order to kind of approximate the variance of the future generation, we are relying on n best individuals, and since these n best individuals are actually sampled from the previous distribution, we are computing the covariance taking advantage of this previous mean, which is a trick. And in order to kind of illustrate the algorithm slightly more detail, it is like this. So we always maintain a pool of individuals, a population in terms of a Gaussian distribution. And we have generation at each time step, and there will be always some scores for each individual. We select like 25% best individuals, which are colored in purple here. So out of these all individuals, we only survive these purple ones. And only using these purple ones, which is illustrated here, we compute the mean, which is the, with these purple individuals and the mean, this green dot over here, mean of the previous generation, not the mean of the new generation, but the mean of the previous generation.